for that, but you will have the other class. P norm of plus 1.96 basically allows you to calculate 0.975. So it's the opposite, it's the upper table. So what I'm doing here is a little bit more complicated because it follows a certain thought process. You remember that we wanted two tails. And the easiest way to get the area under the curve of the lower tail is by basically taking the negative set score of whatever set score you're calculating. And you're doing that by basically setting the set score here to absolute, which drops the negative sign, makes it always a positive value. And then you set the whole thing negative. By that, you basically always get the negative set. Make sense? Doing that basically gets you for P norm. So if you do P norm of absolute 1.96, gets you 0.25, and P norm of minus 1.96 also gets you 0.025. Yes.
I understand if you do actually value there, then you're one put another level.
Because it could be that so you see how these two are different. So you want it to be negative, irrespective of whether the set that you're feeding into your formula is positive or negative. You always want it to be negative. The way to do that, to ensure with the absolute solution that this always is going to be positive, and then you set it negative. Because if you do 1 multiplied by -1, the resultant is going to be -1. If you have -1 multiplied by -1, you have +1. That's why this is such an important trick here. Okay, a good question. Thank you. Okay, so if you do this now as a p-tail test, you basically get the 0.003 that we calculated before. If we do this at in a one-tail test, same principle applies. We get 0.09985. Same story for the smaller one. Please note one thing. So R is not going into the distribution table and is only restricted to 2 decimals. It actually takes the whole range of decimals, and it basically utilizes the function of a normal distribution curve to give you the very exact p-value. And this may differ from what you may read from a distribution table. This may be, it may differ quite substantially, as we will see in the next example. So there's a difference between that. Then we do lower limits and upper limits. We do 514 to 569. That is the 95% confidence interval that we calculated before. Then we do the effect size of 0.42, which is calculated, as we remember, as the absolute difference. So it's the difference between x bar and mu divided by sigma instead of the standard error of the mean. By doing that, we're basically taking out the effect of the sample size that will, quote unquote, artificially lower your estimate of the variability of the sample means. So this is basically how you do the same exercise in R and gets you to the effect size. Also remember the conventions, 0.2 to 0.5, small effect size, 0.5 to 0.8, large effect size, greater than 0.8. No, wrong. Medium effect size greater than 0.8, large effect size. So this would be a small effect size with 0.42. Good. So this was that example. Are there any questions to 729? I think it's considerably easier, right? I think the one-tailed, that requires maybe a second time looking at that and thinking through it a little bit more in detail, but I think it's considerably easy. So let's go to 7.30. We're getting the example from our PowerPoint presentation. Let's copy this into our Excel spreadsheet. So now the values are a little different. So we have now a sigma of 100 again. We have a mu of we have a mu of 500, we have an X bar of 490, and we have an N of 132. So that's the example here, 730 with last time, 490, 500, standard deviation 100. Please make sure that you understand the differences between parameters and statistics. Whenever you think of a population, a parameter basically is only found in a population, which can be a mean that is labeled mu, which is a Greek annotation. And then you have a standard deviation, which is sigma. If you talk about the sample, you're referring to a standard deviation as S or SD, and to a mean as either M or X bar. Please don't confuse those two, particularly in regard of these questions. Read carefully whether you're dealing with a mu or with an M. Know whether you're dealing with a sigma or with an S. That distinction is just very important, because the calculation in the following would be totally wrong. Okay, this being said, let's move on. So 132, we have a calculation here already of the standard error. So basically, standard error we know is the sigma divided by the square root of the sample size is here 8.7. The null hypothesis in a two-sided test is X bar equals mu. Alternative hypothesis, X bar is unequal to mu. The alpha is 5%, set equals X bar minus mu divided by SEM. The X bar, so same error here, X bar equals 490. The lower limit of the confidence interval is calculated as X bar minus 1.96 multiplied by the standard error of the mean, as we know. And the upper limit is 490 plus 1.96 multiplied by standard error of the mean, 507. So now we want to define for a two-tailed hypothesis our null hypothesis, which is basically consistent with what we've done before. So X bar equals mu, research hypothesis X bar is unequal to mu. Our set is, as we know, minus 1.14. Calculated that before. If we go on the on the set score table, we basically find minus 1.1, and here in column 0.04, we want to find minus 1.14. This is 0.1271. We copy this over in the spreadsheet. That basically is now our p-value. However, it's not the complete p-value because we need to multiply it by 2 because it's a two-sided value, so we have 0.25. That's 25% probability that the null hypothesis would be true. 25 probability that the mean that was drawn comes from the same distribution as the population distribution we spoke. It's not 25% that is true. Okay, proportion is this. Percentage would be this multiplied by 100. So that's 25%. And I think that's simple. It's like at this point, I think that should be quite intuitive already. So when we're phrasing now a null hypothesis, so we're starting again with the left side of the hypothesis. That means we're interested that the research hypothesis is interested in whatever's to the left. So our null hypothesis, our research hypothesis is X bar is smaller than mu. Our null hypothesis X bar is greater equal mu. Our set remains the same. Our P is now based on the research hypothesis, everything less or everything under the curve less than this set score of minus 1.14. So we know that this was 0.1271. We know that it's a negative, and this is why it's important that you sketch that out, that you have the normal distribution either in front of your, how should I say, in your imagination, or you actually really sketch it out, because otherwise you may run into getting confused with it. So here's minus 14, so we're interested in everything below that. So you just need to read that very value next to minus 1.14. That's 0.1271, and that's our p-value. So we are actually not rejecting the null hypothesis, but accepting the null hypothesis at a p-value of 5%. So this is the proportion, and this is this multiplied by 100. That's 12.7%. If we are now interested in a right-sided hypothesis, we do x bar smaller equal mu. Now x bar greater than mu is our interest. The set remains the same. And now the p becomes a little bit more tricky, because now we're interested for everything above our set. And that is literally, so we have now, we know this tail, because we have that negative set score. Now we're taking the entire area under that curve as 1, and we're subtracting that left tail. And that is now equals 1 minus, equals 1 minus this p-value. P percentage is now PS multiplied by 100. So 87% speaks against rejecting the null hypothesis and assumes that the sample mean is drawn from the same population distribution, and that there is an 87% that the null hypothesis is not wrong. So here we don't reject, we're not rejecting, or we're not rejecting. Okay, any questions to that? I think once you think the one-tailed hypothesis is true, I think it becomes quite obvious. I like as a didactic exercise to kind of go through the table, because it shows you the different variants kind of in one table, and you can compare and kind of confirm your own thought process on how to approach this intellectually. Any questions on that? No? If not, then we can go back to R. 0.45 is actually a small effect. Okay, 7.3. So starting with line 45, we are now removing on line 45, we're removing everything in the environment. On line 46, we're assigning 500 to our mu, 100 to sigma, 490 to x bar, and n of 133, 32. Line 50 calculates the SEM, again with 8.7. Set score is minus 1.14. The formula here again remain the same. It's 2 times the p norm quantified from an enforced negative set. Basically gets you here to a 0.25. In the one-tailed hypothesis, we're doing the same exercise essentially as we did in Excel. We're basically getting here the p norm of the negative value, so everything less than that. That would be our research hypothesis in the left-tailed example. So this is 0.1252, and this is one of these examples which I mentioned before. So here the rounding kind of really made a difference. So here this is 0.1253 as opposed to 0.1271 as we have found in the other example in Excel. We have 0.87 here in our one-tailed hypothesis that is directed to the right, which is 1 minus our 0.1253. 95% confidence interval, again, consistent with what you've seen in Excel, 472 to 507. The effect size here basically is 0.1. Good. Any questions to anything in R? The practice lab can easily be submitted by clicking on the script. So please go first in the console, press Ctrl and L, empty the entire console. Go then in the script, press Command and A, press Control and Enter, run the whole thing. Then select everything in the console, copy it, open a text edit file. Write in a new text document and save it as STAT1021G hyphen family name hyphen practice lab 3. So what I want to do next is a third example, which is find it. Next example is 7.34. And this example really means to kind of illustrate to you the effect of the sample size. And that's an important example because I mentioned that if you work with really large data sets, it's really not about significance anymore. It's really more about the distribution per se. That's also what we know from last class on Monday, that the variability and the actual distribution is important to keep in mind, the quote-unquote new statistics, to take into account the distribution of that population you're looking at, of that sample population. And so when you have really large data sets, you're quite likely seeing significant differences between the samples, whereas this doesn't necessarily mean that it's clinically meaningful. So it's always important to actually compare the means and look whether these means and the differences in means actually would truly make a difference. If it's just for statistical reasons and it's just because of large sample size, you should state that in a discussion if you write it in the paper. So this example basically means to conduct a comparison between a sample for which you have a mean weight in the sample, and you mean to compare it to the population mean with a standard deviation of 100. So you have an X bar of 150. You have a mu of 160. You have a sigma of 100. You have an N of 30. No, let's not do that yet. Okay. Let's look at this. So we have an X bar of 150, mu of 160, and we have a sigma of 100. So we have an N of 30 for example A. So if we calculate now the standard error of the mean, this would be sigma divided by SQRT of the sample size. We have a set that is basically X bar minus mu. Oops, it's in a bracket parentheses, divided by the standard error of the mean. So our set here is 0.54. So our set is here minus 0.54. If we look this up on the distribution table, minus 0.54, this is here 0.2946. 0.2946. Right. Okay, 0.2946 is P two-sided for a set equals minus 0.54. So this would be 0.2946 multiplied by 2. So that would be 0.5892 for our two-sided hypothesis. If we were to test for a one-sided hypothesis, and we had, let's say, okay, so this is two-sided, this is one-sided, this is now pursuing a null of x bar being greater than mu, and the research hypothesis is x bar smaller equal than mu. We would basically say a p one-sided of p one-sided for a set score equals minus 0.54 is now 0.2946 because it's everything to the left. If I do a p one-sided for an hypothesis where I pursue x bar smaller than mu as the null hypothesis, smaller equal than mu, smaller. The null hypothesis need to be the equal, sorry for that. So it would be greater equal than mu. And the research hypothesis here would be x bar greater than mu. So again, we're testing towards a p one-sided greater than this set score. So that would be calculated as 1 minus our 0.2946. And that is 1 minus 0.2946. That's 0.754. So if we're repeating this now, any questions to that? I think by now we have practiced it quite intensively, and I think it should be fairly clear now. So we have now, for example, if we want to do now a repetition of this example with an n of 300. And we're calculating an standard error of the mean now. We're getting now a sigma divided by SQRT of 300, which gives us a standard error of the mean of 5.77. If we calculate based on the standard error of the mean, we're calculating our set. This would be x bar minus mu in the parentheses, divided by our new standard error of the mean, will give us a set of minus 1.73. So now a p two-sided for minus 1.73 corresponds here minus 1.73 would be 0.0418. 0.0418 multiplied by 2. So that's 0.0418 multiplied by 2. So that's 8.4%. So that's conclusion. Not reject. Equally here, we're not rejecting. So if we're doing the same exercise, and this is where it's getting interesting now, because now we really have a quite large sample size. We're calculating now standard error of the mean, which is basically sigma divided by the square root of 3000. The standard error of the mean has decreased now from 18.3 to 5.8, and is now 1.8. Our set is calculated as x bar minus mu, parenthesis x bar minus mu, divided by standard error of the mean. Was minus 5.47. I don't even need to look at the p-value because I know that this is going to be minuscule p-value. So we're rejecting the null hypothesis at an alpha of 5%, even at an alpha of 1%, if we were to define that. So one interesting exercise, maybe. Oh, no, actually, that's just going to confuse. Okay, interpretation here is reject. We could do one exercise. Let's do that. Okay, but this is clear, right? It's like you're basically calculating the standard error of the mean based on the standard deviation of the sample size. Then you go to the set score, you calculate the set score, you utilize the set score to derive your p-value. And from there, it's really nothing else but an interpretation in which direction you're actually testing and how you define your null hypothesis and your research hypothesis. So it's really more, the arithmetics behind it are like super simple. It's really just a question of how you're defining things and where the concepts are really having most weight in your interpretation. Last thing that I just want to show you quickly is norm.dist. And the reason why I'm showing you that is because there's so norm.dist you can essentially quantify for each value that you're interested in. If you enter norm.dist and you open the formula builder, which you do with the fx here on the left field right next to what you enter, you get here three different fields. You get x1, you get mean, and you get standard deviation. What you get with x1, let's do minus 1.732058. That's our set value from example B. Let's take a mean of 542. Let's take so the difference here, it's 5, no, it's actually wrong, not 542, it would be 10. So let's enter here for the mean, the difference between 160 and 150, which is 10. The standard deviation here becomes our standard error of the mean for the second example B. And if we add an additional field, so it basically, when you click on that plus, basically all these four fields come up. And the last field is cumulative. And if you enter true for cumulative, you basically get here an estimate of what that p-value is. I just want to emphasize you got to multiply it by 2. And it doesn't do that for you. So this is actually an direct estimate. So just like R, also Excel has internal function how you can quantify the P. It does the same thing. It basically maps up that function. It takes the values that you gave it, and it basically calculates the corresponding area under the curve, under that function. And that's the way how to do that in Excel. So as you can see, it's somewhat different from the estimate that R gave us, that the distribution table gave us. So that's all right. Okay. Okay. Okay, so with norm dist, you can basically do this for in Excel. Good. Any questions to any of this? If not, we can do one more example. We can conclude a little earlier. So we have 743. Okay, that's a nice one. So if you're facing an example like that, so if you're using a cutoff of 1.65 and set of minus 1.65, if you have well, that's actually fairly simple. No, that's too simple. Okay, so that's not a good example. So if you have a cutoff of minus 1.65 and 1.65 for a 90% confidence interval, and you have a set of 0.95, are you rejecting or accepting the null hypothesis? Because it's not exceeding those thresholds, of course, you will accept the null hypothesis. If you have a set of minus 1.77, it's exceeding the thresholds for 90% confidence intervals. Of course, you will exceed it. If you have a set statistic that 2% of the scores fall above, of course, you will reject it because it's less than the 10% that you're willing to accept. So you're rejecting the null hypothesis. So I need a better example. Example here. Okay. Let's do this. Eleanor. Good. That's 7.36. And this is one of these examples, right? And let's see, 7.36. So we have height and set distribution. So we have Eleanor, a 15-year-old girl, is 58 inches tall. The CDC indicates an average height for 63.8 inches with a standard deviation of 2.66 inches. So we know that our X bar, our point of interest, doesn't necessarily have to be note. That's a good one. Actually, I didn't mention this yet. It does not have to be a sample mean. It can be any other reference value too. If you have a case like that, where you have Eleanor who has a certain height. So the sample mean essentially is the simple way to look at this, because this is what you usually do in statistics. You compare samples and sample statistics to population. If you have a point value like Eleanor, it's 58 inches, and you're comparing that to a population, you assume her to be the mean of such a sample. So you assume that to be a reference value, and you're estimating this probability around her, around that reference value. So you're still using the same principle and you're using the same approach, but it's in that case, it's not a sample mean, but rather a simple reference mean value. So now our X bar becomes here 58 inches. The mu is 63.8 inches. The sigma is 66 inches, 2.66 inches. So the set score of Eleanor, because you're still doing kind of the same exercise, right? So what is Eleanor's set score? So now you need to go back to, you can't calculate the standard error of the mean. So you try to quantify that set score on your distribution, on your actual population distribution. So if you say 58, now you're not calculating the standard error of the mean. Now you're basically calculating 58 divided by sigma. 58, no, 58 minus mu divided by sigma. That's minus 2.18. So now you want to know what percentage of girls are taller than Eleanor. So if you have minus 2.18, so this is where you can use now your norm dist knowledge. So that new formula that we just discussed. So you basically do norm dist, where X is 58. Your mean is 63.8. Your standard deviation is 2.66. And you want to have this cumulative. But you need to invert it, you need to do 1 minus that. So you know, based on this equation, you know that 98.5 of all the girls are going to be taller than Eleanor. Because with a set score of minus 2.18, is rather on the smaller end. So if we do C, so what percentage of girls are shorter? That's basically this minus 1 minus this. So that's the inverse. E7. How much would Eleanor have to grow to be perfectly average? That's simple, right? So that's mu minus Eleanor. Actually, Eleanor. So now we have D, now we have E. If Sarah would be in the 75th percentile for height at age 15, how tall would she be? How could we know that? It's considerably simple, right? We just need to go for the 75th percentile. It is somewhere here. That's it here. 0.77. So, and we know that the height would be, so it's set multiplied by sigma plus the mean. So this is now 0.77 multiplied by sigma plus the mean. So she would need to grow to 65. So she would be in the 75th percentile if she was 66 inches tall. How much would Eleanor have to grow to be at the, so Sarah is in the 75th%. How much would Eleanor have to grow to be at the 75th percentile? So this is basically F. So now you would do this 65.84 minus Eleanor. I see questions. Okay. Here or no? Well, Sarah is the taller colleague, Elena. She's at the 75th percentile. 75th percentile, you need to go to understand the set score of the 75th percentile. Here?
Yes.
So you basically, you have here 75th percentile. But thanks for telling me that it was too fast.
No, it's a little, where'd she come from? We're talking about Olena, all of a sudden you said Sarah.
Well, it's actually 0.67. Oh my God. 67, God, I'm really. Definitely some better choices. Okay. 0.67. Sorry for that. 0.67. Okay, we have so this is where Eleanor came in, and this is where Sarah joined the body. So we have an example A. We have Eleanor's set score. Eleanor's set score is basically Eleanor's 58 inches minus the mean of 63.8 divided by the sigma. That gets us the set score. From the set score, we can basically quantify the percentile she's in, which is in the 1.5th percentile. So 1.5% of all the girls are smaller than Eleanor. So Eleanor is really rather on the shorter end. So 98.5% are larger than her.
Oh, she's 20.
15. Yeah, she's not the tallest girl, yeah. So now we have with C, we have what percentage are shorter. How much would Eleanor have to grow to be perfectly average? So that's the mean minus Eleanor. So that's 63.8 minus 58. If Sarah is in the 75th percentile for height at age 15, how tall is Sarah? And that's where Sarah joined the body. And if she's at the 75th percentile, we have a set score of 0.67. And that essentially would translate into 65.6 inches. And so if Eleanor would have a growth boost and would get as tall as Sarah, she would grow to be 7.6 inches taller. So that's how you have to go through examples like that. So please make sure you're comfortable with these, because that would be not impossible to come on the test. All right, so 7:32, I guess we're at the end. If there are any questions, let me know now. Any further questions to anything? Yes.
How'd you get C? Sorry.
C, what percentage of girls are shorter? You have quantified the set score of minus 2.16, 2.8. If you go to minus 2.18, minus 2.18, that is, that's this one. No, gotta zoom out, sorry. Minus 2.18, that's this one. That's the 0, that's 1.5%, give or take. Yep. And then 1 minus that proportion gives you how many are taller. Yep.
What do you mean? What do you mean?
Yeah, how many percentage is taller, right? You have 1 is the entire thing. And you have 1.5 or less, then you do 1 minus 1.5, that gives you how many are taller. Yep. All right, great. Sure.
The first quiz, because of my glitch, I ended up getting things wrong, even though I was right. And you said you won't change it, but I
I
looked
did
at
not say I changed it.
what?
I did not say I changed it.
Well, you said you won't do it. You said you won't like. fix
Oh,
it.
I won't change it,
Yeah.
yes.
So I went on Canvas and I looked at all the things and I calculated everything. And because of that one quiz that I like did the right answers and ended up, and it was a glitch. I'm not gonna get an A in the class unless I get 100 on every single thing, just because of that.
How
one
many,
quiz.
how many points did you lose?
I got 35 out of 50, but I did
It's
the,
15 points.
I know, but I did all the calculations, and in order for me to get an A in the class, I need to get literally 100 on every single assignment, which is like not like which is so frustrating to me because I literally like, it was a glitch and I literally got them right.
I did. and then-
So 950 is the threshold for A's, right?
Yeah,
So you still have 35 points, right?
I did like I put in everything.
When I was little.
Well, I didn't see the mine, but
I don't know, I got for mine, I just like I put in everything, and, like,
Yeah.
I'm gonna have to get literally like 100 kids out of every single person. And like I